All right. Hey, everyone. Welcome back for another deep dive.
Yes, welcome back.
And today we're looking at quantum feedforward neural networks.
QFNNs?
QFNNs. Okay.
Yeah.
Based on an essay by Yargo Schneppap.
It's a good one.
And we're basically diving into this world where quantum computing and AI are they're colliding.
Yeah, they're all coming together.
It's exciting stuff. So to start us off, maybe just a quick what are QFNNs?
Imagine like a neural network.
Yeah.
Like the ones we use for image recognition or language processing.
Mm-hmm.
But instead of being powered by just the normal bits,
yeah,
it's powered by the kind of crazy and amazing principles of quantum mechanics.
Okay.
So that's QFNN in a nutshell.
Okay, well, that sounds pretty complex.
It is.
So what's the big advantage of bringing quantum mechanics into this?
Well, classical computers, the ones we use every day,
right,
they rely on bits, 0 or 1. But quantum computers, they're different. They use these things called qubits.
Qubits?
And this is where it gets really interesting.
Okay.
These qubits, they can do something called superposition.
Superposition.
They can be 0 and 1 at the same time.
How is that possible?
Well, that's quantum mechanics for you. It's kind of strange, but it's really powerful. And so this ability to be in multiple states at once.
Right.
And also this thing called entanglement, where these qubits, they get all interconnected.
Okay.
It lets these quantum computers they do these calculations at speeds that would just blow a classical computer out of the water.
So we're not just talking like a little speed boost.
No.
Like this is
exponential speed increase for certain problems. Like, for example, there's this thing called Shor's algorithm.
Right.
It's a quantum algorithm, and it could crack like the encryption codes that protect all of our stuff online, like our bank transactions, in a fraction of the time a normal computer could.
So like cybersecurity experts are quaking in their boots right now.
Yeah, I think they are.
But back to these QFNNs.
Yeah.
How do they actually use this quantum power?
So instead of those normal neurons, that are like little switches,
right, on or off,
QFNNs use those qubits.
Okay.
And these qubits, with their superposition abilities, they become the building blocks of this whole quantum neural network.
I'm trying to picture it.
Yeah.
But it's a lot.
It is a lot. It's a lot.
It's hard to visualize.
Think of it this way. It's like a network of these neurons, all interconnected.
Right.
But they can explore all these possibilities.
At the same time.
At the same time, it's like having a neural network that can just...
It's like multitasking.
Yeah.
On a massive level.
It's like parallel processing on a crazy scale.
Okay, I see the potential here. So what kind of tasks are good for this parallel processing?
They're really good at what we call optimization problems.
Optimization? Okay.
Where you have to find like the best solution out of a ton of possibilities.
Right, like a ton.
Like finding the fastest route for a delivery truck.
Right.
Or, optimizing a financial portfolio, all those kinds of things.
So instead of checking each solution, like one by one.
Yeah, exactly.
The QFNN can look at a bunch at the same time.
Cut through all that noise and find the best solutions so much faster.
That's super powerful.
It is. It's incredible.
But how do we build these quantum neural networks?
So they're complex.
Yeah.
But the basic building blocks are these things called quantum gates.
Okay, quantum gates.
They act on the qubits, and they control the information flow.
So they're like the connections between the neurons, but instead of like sending a signal, they're messing with these qubits.
Yeah, exactly. And by arranging these gates in different ways, we can make these quantum circuits.
Quantum circuits, and they're really the core of any quantum computation.
Okay, so we've got qubits, we've got gates, we've got circuits.
I've got it all.
It's like a whole new computer.
It really is.
But how do we actually train it to do something useful?
So training a QFNN, it's similar in concept to training a regular neural network.
Okay.
But it is a lot more intricate.
Okay.
It involves adjusting all these parameters of the quantum gates to make it perform well.
So we're still feeding it data.
Yeah, you're still feeding it data
and letting it learn, but now we're tweaking the quantum gates instead of the connections between neurons.
Precisely. Yeah, that's a great way to put it.
Okay, and I imagine that's pretty hard.
Oh, it's really hard.
And that's where the real challenges are.
Yeah, this is cutting edge stuff. So it sounds like we're still in the early stages of figuring all this out.
We're just scratching the surface.
Well, let's maybe shift gears a little bit and talk about the applications.
Oh, yeah.
Like what are some of the areas where this technology could really shine?
So many areas, so many. But
give me some good ones.
Let's start with medicine and material science.
Okay, yeah, let's dive into those. I'm really eager to hear more about those.
Okay. Yeah, so before we jump into those applications, there's one more thing I want to touch on from the essay.
Okay.
And that's this idea of quantum entanglement.
Right. You mentioned that earlier.
I did.
But I'm still not totally sure what it means.
Okay, so imagine like two qubits that are linked in a way that they share the same fate no matter how far apart they are.
Okay.
So if you measure the state of one, you instantly know the state of the other, even if they're like across the universe.
Wow, that's like sci-fi stuff.
It is. It's mind-blowing. It's one of those.
How does that play into QFNNs?
So entanglement, it lets these qubits work together in ways that regular bits just can't.
Okay.
It creates this like synergy that just boosts the power.
So it's like they have like a secret communication channel.
Yeah.
Like they can coordinate.
Exactly. And that's how QFNNs can tackle these problems that would take a regular computer forever.
Right. Like they would never be able to solve them.
Not in any reasonable amount of time.
Okay, that makes sense.
Yeah.
So it adds like another layer of complexity to these QFNNs.
Yeah, it's one of the things that makes quantum computing just so different.
Right.
It's so powerful.
Okay, well, you've definitely made me more curious about these applications.
Okay, good.
You mentioned medicine and material science.
Yeah, so let's start with medicine.
Okay.
Imagine being able to simulate the interactions between molecules at like the atomic level.
Yeah.
Something that regular computers they struggle with.
Why is it so hard for them?
So as you zoom in to that molecular level, the number of interactions, it just explodes.
Okay.
Every atom is interacting with its neighbors.
Right.
And it's like trying to track a billion billiard balls all colliding with each other.
Okay, that sounds like a nightmare.
It's a computational nightmare.
Yeah.
But QFNNs, with their ability to explore these multiple possibilities, they could simulate these interactions way more efficiently.
Okay.
And this could lead to like breakthroughs in drug discovery.
Right.
We could design drugs that target specific diseases.
So we could develop treatments that are tailored.
Yeah, that's the dream.
To an individual.
It's personalized medicine where the treatments are just for you.
Wow.
Maximizing the effectiveness and minimizing all those nasty side effects.
That would be huge.
That would be a game changer.
What about material science?
Yeah. So imagine being able to design materials with specific properties like superconductivity or incredible strength by simulating how the atoms and electrons behave.
So you're saying we could create materials with properties that don't even exist?
It's possible.
Yeah.
We could have materials for renewable energy
or
lighter and stronger aircraft.
That's incredible.
It's really exciting stuff. And these are just two examples. Like the applications go way beyond that.
Okay.
Like finance, logistics, even AI itself.
Okay, let's talk about those. Like I'm especially curious about how QFNNs could impact AI.
Yeah.
What are some of the ways they could be used?
Well, one area is machine learning.
Okay.
They could be used to develop algorithms that learn way more efficiently than traditional machine learning algorithms.
So we could see even more powerful AI systems.
It's a definite possibility.
Because of this quantum boost.
Yeah, imagine AI systems that can see patterns.
Yeah.
That we can't even see or make predictions with incredible accuracy.
That's both exciting and a little scary.
It is.
But aren't there some big challenges?
Oh, absolutely.
That we need to overcome before we can actually see this happen?
Yeah, there are some big hurdles that researchers are working on right now.
Okay, well let's dive into those.
Okay.
Like what are some of the biggest obstacles? All right, welcome back to the Deep Dives. We've been talking about QFNNs, and it sounds like there's some big challenges to actually making these quantum neural networks a reality?
Yeah, for sure. One of the biggest ones is this thing called decoherence.
Right. Remind me what that is again?
So think of it this way. Qubits, they're super sensitive.
Okay.
Like snowflake.
Yeah.
Any little disturbance, heat, vibrations,
right.
Even like stray electromagnetic fields, they can mess up these quantum states.
It's like the qubit's losing its quantum power.
Yeah, exactly. It loses that ability to be in those multiple states.
Right.
And when that happens, errors get into the calculation, and it makes the results unreliable, and it's a big headache.
Yeah.
For researchers.
So how do we protect these qubits from all this noise?
Well, researchers are working on a bunch of different strategies.
Okay.
One approach is to just make better qubits that are less sensitive.
Okay.
Another approach is to develop error correction techniques.
So it's like spell check.
Kind of, yeah.
For a quantum computer?
Kind of, but it's way more complicated. It involves using like extra qubits and really smart algorithms to protect that information.
Sounds like a big engineering challenge.
No, it's huge. It's a huge challenge, and it's one of the key areas that needs to improve before we can build these large-scale quantum computers.
So we need better hardware.
Yeah.
Better error correction.
Yes.
What else? What other challenges are there?
Well, we also need to develop better algorithms that are specifically designed for these QFNNs.
Okay.
They need to use these quantum properties, but also, deal with the limitations like decoherence and the fact that we don't have that many qubits yet.
It's like trying to write software for a computer that's not even finished yet.
That's a great analogy.
Yeah.
So we have to be creative and find ways to use what we have while we're building these better computers.
And Schneepat, in his essay, he points out a few other things too, right?
He does, yeah. He talks about the need for more research into how these QFNNs actually work.
Right.
Like, how do they learn?
Yeah, like what are their limits?
Exactly. There's still so much we don't know.
So it sounds like there's a lot of basic science that still needs to be done.
Absolutely.
Before we can really see the potential here.
It's a field that's full of unknowns.
Yeah.
Which makes it really exciting.
Well, I'm definitely convinced that these QFNNs could be revolutionary.
Yeah, I think so too.
But it sounds like we're still in the early stages of this quantum journey.
We are. We're just at the beginning.
Yeah.
It's going to take time. It's going to take ingenuity.
It's going to take a lot of collaboration.
Well, I'm excited to see what the future holds.
Me too.
For QFNNs and for quantum computing in general. It's been a fascinating conversation.
It has.
Thanks for guiding us through this complex topic.
Happy to do it.
And to all of our listeners, thanks for joining us on this deep dive into the world of quantum feed-forward neural networks based on the essay by Jark O. Schneepat. And we'll catch you next time for another deep dive.